All right, what's up, my YouTubers? So we're going back to mechanics of materials again, and here now we are going to be talking about deformation due to axial load. So in this playlist of mechanics of materials, I've got stuff on stress, strain, uh, I got to throw in some stuff on stress strain curves and all this, but we've covered basic stuff, and finally we're getting into something that's a little exciting, a little maybe a little bit more interesting here, and we're going to be talking about deformation due to axial loading. And here, hopefully by the end of this video, you'll be able to calculate deformation of an axially loaded member. So just to start off, let's consider a rod. So bam, I got me a rod here like this. And let's say the rod here is fixed to one end and it has a constant area cross section. It's some material. It's a uniform homogeneous or homogeneous material. Homogenized milk. Anyway, and then like here, I've got some length associated with it. L, bam, bam, L, and then I have a force applied, some external force, which I will call P. And and I know that when I want to examine this on the inside over here, I'm going to have, I'm going to end up drawing a free body diagram there. Here, if I make a cut at that blue line and I look right here and I look at the right side of that cut, and I would see that here I have this external force P, and at some distance away, in fact, really all the way across anywhere, I have this internal normal force, which is equal to P. And you would tell me that the stress here, the stress on this cut or at this face right here is equal to N divided by A, which in this case for just a single axial load is P over A. And then the deformation or the strain right here, the deformation that results here, let's see, if I apply some load here, I'm likely to cause some deformation, we'll say delta right here. And you would tell me that the strain is the change in length divided by the original length. And I have my two relationships here, and if I want to put them together, and here's where we call on Robert Hooke and his law, Hooke's law, which is really, we know sigma is equal to E times epsilon. And here, if I substitute the P over A and the delta over L, I find here P over A is equal to E times delta over L. And if I and we know this is the deformation of the rod or the member, deformation here. This is what we're looking for, and that becomes, if I just rearrange, delta equals, if you don't know what the applied load is, NL over EA, or here, PL over EA. You see some in a lot of textbooks, PL over EA, and this is the deformation due to applied load. This only works for, this has some assumptions in it. One, a constant cross section, i.e. the area is constant. Okay. The axial for the internal axial or internal normal force, internal normal is also constant. Normal force is constant. And I have the same material all throughout, same material. Okay, it's homogeneous. All right, so this equation assumes constant cross section and constant internal normal force. Okay, so bam. So this is this is a basic equation, and really what we want to do is look at this in a more general sense. So this is the example, and this is really this very useful equation that gets used most of the time, because a lot of the problems that we're going to look at have constant force or constant internal normal force and a constant area, and it's going to be over a predefined length. The but let's reconsider here a rod here. So in general, I have this rod that's fixed to the side or some structural element, and it has a varying cross section of some kind. So here, bam, like this right here has a varying cross section. I'll call this axis X, my X axis here, and really I have a cross section that's a function of X. We'll say the material is still the same, so the modulus of elasticity is the same all throughout. And let's even put in like a distributed or a uniform axial force, okay, as well as a concentrated force at the end here. I'll call that P1. Okay, and so this is like some distributed P of X, some distributed internal axial load, or not internal, I'm sorry, external axial load, right? And then I would have a reaction here, which I'll just call P2 right there. And now if I look at a specific segment here, so if I just look at a segment, oh, well, real fast, you know that this thing will deform some distance. This thing will come out and it will deform some distance. We'll call that delta. And that's the deformation we want to find due to all this loading. So here, let's examine like a small slice of this section right here at some distance away. So here, some distance from the origin, some reference right here, we'll say at x. And this has an incremental width dx right here. And so if I zoom in on this cut right here, here is my cut section, and it has a width dx right here. And I know that even this will deform, will have a slight deformation, if you will. Let's see, how will I draw this deformation? It will be like, oh, we'll just, like that. We'll just say it deforms out a little bit. You know, we'll have, let's see here, and it'll be boom, 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 like that, okay? So some deformation that will occur, and I'll call this incremental deformation, d delta, right here. I'm going to have an internal force, which I will call that n of x at this location x. N of x is an equilibrium here. And the stress here, the stress is, the stress at this point, the sigma at x is equal to n of x divided by the area at x, right there. And then the strain is the change of that little increment, okay, of that little different, or the element right here, over dx, right here, d delta dx. And then again, if I relate the two using Hooke's law, then I would have this here using Hooke's law again. Hooke's law, not Captain Hook, but, you know, Robert Hooke, right? It's like a friend, almost. You know, you use Hooke's law so much, you wish he was your friend, right? Anyway, but here, the sigmas of x is equal to E times epsilon at x. Oh, this is a function of x, or the strain at point x right here. This would just be n of x over E a of x is equal to d delta over dx. And, you know, this whole thing, that dx is probably screaming integral, right? So here, this d delta, I want to take the integral so I can calculate. I want to sum up all the little increments here. Bam, n of x e a x dx right here from 0 to L for the length of this. Oh, I didn't find a length right here. Let's call that length L right here. And it would just tell me that this deformation, delta, is equal to, you know, this integral right here, n of x e ax dx right here. And this would be it. Bam. And this is my general deformation. This is my general equation for deformation of an axially loaded member. And another thing to remember is that really this delta, this deformation, is a relative deformation, okay, from the deformation of one end relative to another end here. And it's just this delta right now in this case represents, you know, the deformation of this end relative to the fixed end here. Okay. And really the let's see, one other thing to note is, you know, a lot of times this PL over EA suffices in many problems. And so, you know, but what happens is sometimes you have, say, in a rod here, let me draw this rod. Oh, I forwent my straight edge. But here, I might have, you know, various axial loads, P2, P1, you know, at different segments. And so my internal axial force here is one, you know, one value, we'll call that N2, and then another here, N1. Okay, so I have different internal axial forces, and what you're going to want to do is take segments where the internal axial force is constant, and you'll be able to sum and calculate the deformation associated with each segment. Okay, so here this might be like L2, L1. Let's say the areas for our sake are constant, and we have E, and so my deformation here, my total deformation, will be the sum of Ni Li over Ea. Okay? And this would be I equals 1 to the number of segments or that have constant axial force or axial load. And that's really how, this summation equation is also another popular application that I'll do an example on in a second. Okay. Hopefully you enjoyed that explanation. If not, well, you didn't. But don't judge me, judge yourself and make it happen. All right. Enjoy mechanics.